We are taught that gravity is a fundamental warping of a continuous space-time fabric. But if we evaluate the strict mathematical boundaries of physics, a different mechanism appears. Gravity behaves as an emergent property, the macroscopic shadow of a discrete, number-theoretic data stream. This image displays the two master equations of this framework. On the top is the emergent Newtonian gravitational constant, and below it, the effective cosmological constant. Instead of being arbitrary physical parameters, both are derived entirely from pure mathematical inputs. This flowchart traces the derivation bridge. Starting at the top, we evaluate the spectral expansion of the vacuum. As this action pushes forward onto an arithmetic manifold, data scales into localized curvature, perfectly matching the classical Einstein-Hilbert action. Here, we break down the anatomy of the gravitational constant itself. The equation relies on three core variables. The first block shows the ultraviolet cutoff scaling, where gravity is inversely proportional to energy. The middle block is the arithmetic mass shielding, governed by the Galois L-function, and the right block tracks fiber volume suppression, represented by the parameter beta. Reading across these panels reveals a strict physical mechanism. The absolute strength of gravity is dynamically tuned by the arithmetic distribution of prime numbers and the topological capacity of hidden internal geometries. This graphic shows the baseline calculation. We start with a standard SU3 gauge sector, evaluated over a smooth genus 1 curve. Passing these parameters through the geometric and arithmetic screens in the center generates a precise volume constant and a specific L-function target. Evaluating those exact invariants yields a coupling constant of roughly 2.067 times 10 to the negative 38 per giga-electron-volt squared. Converted to macroscopic units, this maps directly to the classical physical strength of gravity measured in our universe. This table compares what happens when we scale the topology. If we increase the base curve from genus 1 to genus 2, the internal configuration space experiences a dimensional explosion. A simple one-dimensional torus expands into a 10-dimensional complex variety. Looking at the genus 2 column, this phase space swelling drives the volume constant up by a massive margin. Because that volume sits in the denominator of our equation, the macroscopic strength of gravity is suppressed by a factor of roughly 420. That volume constant relies on the factorial growth of the gamma function. So if a genus 2 curve suppresses gravity this significantly, we have to calculate what happens when the genus scales to 3 or higher. The final column shows a mathematical turnaround. Beyond genus 2, factorial decay completely dominates the fraction. The volume constant collapses towards zero, forcing the gravitational coupling constant to explode toward infinity. What looks like absolute decoupling at genus 2 is actually a critical phase boundary. Beyond it, the data stream is so strangled by high-dimensional topologies that the smooth space-time fabric collapses into discrete, strongly coupled quantum nodes. We can test this boundary from the other direction by manipulating the arithmetic sector. Instead of changing the geometric genus, we introduce a single ramified prime place, the prime number 3, into our data stream. This diagram tracks the dual effect of that ramified prime. On the left, the local L function collapses, removing a layer of information screening. On the right, the period matrix develops a logarithmic defect, causing the fiber volume to pinch and compress the metric field. These two pathways merge into a localized ramified well. At this exact arithmetic coordinate, the gravitational constant spikes, becoming over 4 times stronger than the surrounding unramified vacuum. The horizon cage diagram on the right models the physical result of that spike. The local metric intensification creates an arithmetic black hole. The localized gravitational pull forces the escape velocity to exceed the speed of light, permanently trapping data packets inside a cosmic loop defect. Gravitational singularities are not structural failures in the space-time fabric. They are exact geometric consequences of a data stream processing its own arithmetic boundaries. Having mapped these localized anomalies, we must account for the vast spaces between them. To determine the uniform background energy of this universe, we evaluate its two-loop quantum fluctuations. This formula details the balance. The hook diagram on the left probes the self-interaction of the datasheets, yielding a positive geometric energy density. The theta diagram on the right captures derivative exchanges between those sheets, acting as a negative arithmetic screening mechanism. This evaluation path runs the numerical threshold check. By plugging in our precise invariants, we see the geometric volume term is strictly greater than the arithmetic L-function threshold. The residue is strictly positive, meaning the universe naturally generates a de Sitter accelerating background, dark energy. This chart reveals a structurally sealed crystal potential landscape. The geometric arithmetic balance yields an unramified smooth plateau of continuous expansion. But moving along the spatial axis, periodic ridges drop into deep wells, where ramified primes force the metric to intensify, condensing into physical matter.